All right, well, my name's Kurt Larson. I'm a member of the technical staff here at Sandia, and I thank you for the opportunity to come and talk to this conference. I think this is probably the oddest titled talk I've ever given, and it's going to be fun to talk about. I am neither a neuroscientist nor a hardware device developer, and so I wanted to just mention a bit about how I came to be here today. But about 5 years ago, I was leading a team looking at basically smart sensors, a smart sensor problem that we had. And we evaluated an algorithm that was basically a Bayesian detection algorithm. And this was in satellite sensors. We were trying to figure out algorithms that could go into future satellite platforms. And the Bayesian algorithm worked really, really well. It compared as well as any other algorithm we were looking at for the particular problem we were trying to solve. But it was obscenely computationally intensive, and there was no way we were ever going to put it into the weight, power, and computational complexity of a satellite platform. And so that sort of got shelved. We wrote it up and kind of got shelved as, you know, an interesting failure. And then about 7 months ago, someone forwarded me the DARPA upside proposal, which was about building Bayesian type computation, and I wasn't even familiar with that, not being a hardware guy. And so that got interesting to me, and then I ended up meeting Murat and a whole bunch of other people who were following up with that, and read Ben Vigoda's paper about low power Bayesian inference and so forth, and it just kind of snowballed into me working kind of up on what do we do at Sandia that could benefit from these kinds of hardware devices that are being developed, and that's what this talk about today. So basically, I'm going to go back. I don't want to talk about that just yet. Basically, it turns out that when I read Ben Vigoda's paper and we got into talking about Markov chain Monte Carlo calculations, that is a huge domain for Sandia, and it's something that's very computationally intensive to calculate. It's not done as much as we'd like to be able to do it, and if we had hardware that could basically accelerate the process for computing Markov chain Monte Carlo, basically uncertainty quantification problems, that a whole bunch of application areas might benefit. I'm going to go into some of those today. The other thing that was going on is not only the Ben Vigoda stuff, but also some of the things that Murat talked about the other day, yesterday, when he described the kind of massive interconnection optical framework that's being developed at Sandia and probably other places as well, that might break us out of, you know, one computational element, one low-level device being able to see maybe 10 other devices at the most, to possibly being interconnected with up to 10,000 other devices and things like that. And if I'm getting the numbers wrong, it's because I don't know them. But in any case, so I started looking around Sandia and looking at, well, what can we do? You know, where do we want to do these uncertainty quantifications? Where do we want to do these things that have these massively interconnected possibilities? I'm not going to put out any architectural frameworks or anything like that, but I'm just going to try to show some application domains that could benefit from new architectures. One of the things that is interesting to me was Lloyd Watts yesterday talked about how in neuroscience that how he was able to take a very detailed understanding of a low-level system, the cochlea, and how it solves the spatial audition problem, and bring that into a useful device. And I guess what I'm saying here is that as these new hardware devices are being developed that go towards neuroscience, it may be that there are perhaps not neural applications of these things, but there may be other computational architectures that are transformational and revolutionary, even though they may not satisfy all the interests of the neural sort of the neural problem, which is certainly very exciting. So basically, you've heard from Mike Volley and Rob Leland some of Sandia's interests. I want to go back into that a little bit just to set up my talk. You know, we have the traditional very strong interest in nuclear weapons, basically anything to do with nuclear weapons, perhaps except the physics package, which are which are handled up at Lannell and Livermore. But we also have, for a long time, and it's still expanding, interest in national security. And kind of coming out of our national security expertise has also come up basically out of our national security and also our nuclear weapons expertise is non-proliferation. So getting into all aspects of nuclear and weapons of mass destruction non-proliferation issues. Finally, energy and environment, and then basic research to support those kind of five domains. So I'm going to get into some of that in this talk. So the first thing to notice I'm going to talk is about basically partial differential equations, wave equations that can be solved, and some of the applications that we have for uncertainty quantification. Everything I'm going to talk about is basically open type stuff, but there are big areas of application in this in kind of the national security and the nuclear weapons with probably a different emphasis. But in any case, this is recent news, North Korea's third nuclear test. Basically, Department of Energy has a policy. It's not a goal, it's not an objective, but it's basically a policy statement that no nuclear explosion will go undetected. No matter who tries to do it, no matter where it occurs, no nuclear explosion will go undetected. It's essentially the same policy stated by the Comprehensive Test Ban Treaty Organization as well. But basically, so nuclear testing is continuing. What we get interested technically are things like this. This is the Comprehensive Test Ban Treaty Organization's plot of the epicenter and uncertainty bounds on those 3 detonations by North Korea. And basically what we want to be able to do with our nuclear monitoring for nuclear explosions is we need to be able to not only detect the nuclear explosions, we also need to be able to distinguish them from earthquakes, which there are some very, very significant differences between an explosion and an earthquake, but also things like completely legitimate conventional explosions that might occur at mining activities. Some of those explosions get to be very large. So one of the things that we need to do, and we do it here at Sandia, this is actually, I'm in Department 5563, which does some of this, is we need to basically understand the structure of the Earth in 3 dimensions in very high detail. This is an example of one of the models that we use to do this. One of the things that we do at Sandia is develop technology to come up with uncertainty in travel times, which is something that very few places do. This is kind of a diagrammatic model. If we actually plotted the real model that's used with the black lines tying the computational elements together that we actually use, you would see no color. We have to go to very high spatial discretization to get these calculations to the level of fidelity that we really need. But basically what we're trying to do is to infer the structural properties of the crust and especially of the mantle to very high precision so that we can infer, basically get those error bars on those locations and the discrimination properties as best as possible. So the output of the model, here's a 100-kilometer depth variability in the seismic wave velocities through the Earth. And this is one of the higher fidelity models that is available anywhere in the world. And again, what we're looking at is getting at the variability. What we'd really like to know, and which we haven't been able to get to, is the uncertainty on all these elements. And we can't get there because partly the computers that we use can't do the uncertainty quantification fast enough to make it meaningful. And so if we could come up with some sort of architectural improvement to the computers that we use so that they would support the uncertainty quantification, we might be able to improve our product even further. And then basically just to show the 3-dimensional nature, this is a slice from that model extending from the crust down to the top of the liquid core. And again, it's just, this is a static deterministic inversion of seismic waves from seismic stations all over the world for both earthquakes and explosions, but it doesn't include the uncertainty. And we'd like to be able to get at that uncertainty. So one area that we'd be interested in is basically uncertainty quantification for wave equations. You guys all know wave equations are ubiquitous. They're, you can't hardly do an engineering or scientific discipline without getting into partial differential equations of some sort. And certainly in our nuclear weapons and other areas, we are very interested in uncertainty of materials. You heard Mike Volley mention yesterday that the nuclear weapons area is getting into things like margins and uncertainty of our knowledge limits and things like that. And that's all asking for ways to calculate Bayesian type statistics very, very efficiently. So moving on to other areas, when we get into kind of environmental energy type issues, we get into big problems pretty quick. This is an example, or basically this is another big deal. This is, anybody guess what that is? That's the East Coast the day before and the day after Hurricane Sandy, as seen from space. So you can see that when you've got basically Boston all the way down to Washington, D.C., and you know, the night lights as visible from space is significantly impacted in the course of that event, that it's a big deal when a hurricane makes landfall. It's not, you know, not a surprise to any of us. But one of the things we do at Sandia, it's becoming an increasing area of business for us, is to help the federal government understand, basically in predicting and reacting to huge events that impact our infrastructures, impact these things that we all depend on. One of the big deals was that in 2005, I believe, was Katrina. Sandia was one of the few places that we had this capability of looking comprehensively at these big events. Sandia was one of the few federal agencies that had actually correctly predicted that New Orleans could be flooded from that event. And so that was one of the things that put this capability on the map. But basically, if you look at what's going on here when something like a hurricane impacts a population, the complexity of the problem is basically beyond any single person's comprehension. And one of the things that we're working at here is how do we represent, how do we simulate, how do we develop not only policy planning in terms of what sorts of things should we be doing proactively to respond to events like this or prepare for events like this, but also crisis management. And it turns out that we have a group of people at Sandia that during Sandy were on call for about 2 weeks before until about 3 weeks after, answering questions such as, this is one of the questions we actually got in the middle of the night. New Jersey Power Company is able to restore power to one of the 7 refineries in New Jersey. They were all taken offline by Hurricane Sandy. Which one should we turn on power to first? Which one gets the most resources back online to the population? So these are big problems. They affect people's lives, and they're becoming more and more important to federal policy planners and crisis management. So we have this federal structure called the National Infrastructure Simulation and Analysis Center. It was born out of basically an interaction between Los Alamos National Laboratory and Sandia National Laboratory that started before 9/11. But after 9/11, it was recognized that this is a pretty important thing. It got elevated up to the Department of Homeland Security. Basically, the Department of Homeland Security has identified these 18 infrastructures called critical infrastructures, and Sandia is part of that federal structure that's looking at trying to understand these structures, trying to look at how is it that they form, how is it that they behave, how is it that they fail, and what are the consequences of failure, and what can we do proactively and during a crisis to do something about that. So basically we have the infrastructures over on the right on this image, and we have hazards, a variety of things on the left, and the interactions playing out in terms of social, cultural, people's lives. Another thing that's playing into this, which was kind of alluded to by several presenters earlier yesterday, is that these are very complicated systems. So we have an initiative at Sandia that's basically part of, or included in NESAC, but separate from it, and not wholly contained, which we call the Complex Adaptive System of Systems Engineering. Basically, we have our complex systems down here, kind of a hierarchical structure, ecosystems, enterprises, infrastructures, economies, societies that collectively form these adaptive system of systems. We have perturbations, the things that are not normal parts of the behavior of these systems but can come in and cause problems. And then we have our aspirations. What is it that we want to accomplish in our policy or our management of crisis to basically reduce the impact of the perturbations? And so we're looking at these problems from this kind of a perspective. This is enormous. We don't have a model of all of it, of course. But when you start looking at problems this way, I guess I didn't know I had that dynamic slide in there. Okay. Basically, the way these systems happen is that here's a model that was built up of the petrochemical industry. Basically 8 elements, and kind of using a software modeling technique, various types of relationships among these 8 elements. It's pretty simple. It's easy to get your head around that and think about it. But when you bring that into a network where you actually populate it with the real physical entities that exist out in the nation, it starts looking very complicated. Okay? And one of the things about complex systems is that it's not completely chaotic, but there are interactions and things of behaviors in this structure that are not predictable. There are aspects of these systems that cannot be predicted. And one of the aspects of these things that's difficult to understand and kind of is defying conventional wisdom but is becoming increasingly appreciated is that a lot of these complex systems, the severity of events does not fall off in kind of a bell curve shape. The severity of events is the occurrence of severe events is much more common than we expect when we think about it from typical statistical distributions. So we have emergent structure from very simple definitions, and we have emergent behavior that is more complicated and perhaps more consequential than we expect. So big events are not rare. This has been noted in lots of natural systems, but it's also being noted now in these manufactured or anthropogenic systems. So one of the examples here is payment systems, basically financial networks. When we look at the U.S. financial network in terms of all the banks and all the interactions in a daily basis of $1 trillion being moved around, this is what it looks like when you don't pare it down. But when you pare it down to kind of the biggest actors, we get this scale-free network where we have 2 or 3 banks that are handling a huge amount of the traffic. A whole bunch of other banks, this is basically the Federal Reserve System and the principal commercial banks on the outside, forming the backbone of the structure. And it's a scale-free network in the sense that these entities that are handling most of the traffic are kind of attracting that traffic, because as they get bigger, they attract even more, and the bigness gets bigger. Okay, well that leads to these cascades. This is kind of the simple model that demonstrates it. And here we have basically the U.S. has this system, the Europeans have a similar system but different. We've got these small world interconnections between, which are basically the foreign exchange between the big banks. One of the things that's been interesting in this analysis is that this system it's not inherently unstable, but the constant innovation by the marketers of the financial products, basically the innovators in Wall Street and elsewhere, those are constantly destabilizing influences. So one of the challenges when thinking about policy in response to this is that how can you implement policy for managing things like this, recognizing that there are going to constantly be destabilizing influences. There's constant innovation of people basically trying to figure out how to make money in the latencies and so forth in these systems. Another system that's relatively easy to understand but notoriously difficult to model and get at is something that we haven't done a lot of work in, but we've kind of mapped it out, is the food distribution network. And right now there's kind of this problem of if a supermarket, if some people start getting sick somewhere, it gets traced back to where they bought the food fairly quickly. And perhaps back to what food they bought, and then basically that food gets yanked off the shelves everywhere in the country. And that's a huge cost to people who are looking after their own health. I mean, it's certainly conservative, but it's a huge cost to the entire nation as well to basically yank all the food out. So one of the things we're trying to work on is, you know, are there better ways to basically monitor the food network and so forth to come up with better ways to manage those types of crises? Okay. The problem with this one isn't that it's inherently unstable, it's just that it's dynamically changing all the time. So if you could monitor, where should you monitor such that it's robust to the constant changes in the suppliers and so forth, but also not staying too far behind. So I'm bringing up these examples not because these are the particular problems that are really necessary to solve, but that these are getting pulled up into federal policy. These kinds of things are getting attention. So here's another example. Back in 2006, when the H1N1 virus there was a lot of worry that it was going to jump out of its natural situation into humans, and that it was possibly virulent enough to kill as many people as the 1918 flu. Work we did at Sandia also kind of helped put this whole area on the map for us, was to first model the social networks within which this transmission might occur. So we had teens, which are in red. We had young people, basically children, in the light blue, parents in the dark blue, and adults in black, and seniors in dark blue. And so we put together the networks, and we combined it with the type of models of disease transmission that were being used elsewhere. And in approaching this model, this was all done between late October and mid-December. Unfortunately, this doesn't show up very well. But basically, this is a kind of a dendritic pattern of all the transmission of all the diseases, of the disease through a population. And it turned out that the model, without much calibration, kind of hit the numbers right from past pandemics. And it got pulled up to the White House, and basically the White House added the notations, the White House staffers added the notations where this is transmission via an adult pathway, and the red are transmission via teen pathways. And the point being that at the time there was not much policy around what we could do as a nation to respond to a pandemic influenza. And what this type of approach to this problem helped recognize is that, I'll just throw these up there, is that basically by closing schools and keeping the kids home, basically breaking down the social network of the kids, we would be able to dramatically reduce the number of infected people from the disease. There's another one that's kind of getting into use of these types of social network models for things that are sort of a lot less concrete than disease transmission or payment policy and things like that. This is work that's going on right now. The FDA is responsible for regulating tobacco, and they're concerned about basically population health. And one of the things that we're working with them on is how can we basically look at the dynamics of the prevalence of smoking in the population versus an initiation threshold. This is the probability that people begin smoking in the presence of a variety of media campaigns. So if we have basically the baseline model, we look at what happens if there's only education, what happens if there's only advertising, what happens when they're in competition, what happens when there's various sequences of education and advertising. Well, this is interesting. We're sort of coming out at prevalence and so forth, but it doesn't really get at the health impacts. So models like this, which are complicated and so forth, are being combined with models like this, which are implemented throughout population aging studies to try to come at what are the health impacts of smoking, and how can the FDA help create regulation and public policy that looks at new products coming into the market, looks at prevalence of advertising, looks at the impact and effectiveness of education and so forth. And what happens is we get to outcomes or model outputs like this, which are not fantastically complicated, but they're looking at the effectiveness of what happens in the population over time with education, with increased advertising, increasing youth initiation, or just small spikes in advertising and things like that. So again, these models aren't huge. They don't require supercomputers right now, and we're getting at also things like sensitivity analysis, uncertainty analysis around these models. This is looking at the impact of the proportion of immigrants who smoke, uncertainty in the models due to the stochastic variability of the uncertain parameters. And the point isn't really that this particular model is all that complicated or requires a huge amount more computation. The point of showing these examples is that this type of modeling is penetrating into public policy. It's penetrating into the people that are making decisions about how people live, how people interact, and it's having, basically there's a pull from the policymakers in Washington where they're wanting this kind of product when they're trying to figure out what sorts of regulations, what sorts of things should be done, both in policy that they advocate, policy that they implement, as well as crisis management and so forth. And so yesterday, Mike Volley talked about how weapons testing has migrated from basically experimental tests that were done in the atmosphere originally and then underground eventually. It migrated to computer simulation. And one of the things that I'm suggesting is that if we had computational architectures that were capable of dealing with the uncertainty analysis in models like this, that were capable of dealing with network formation, capable of dealing with interactions and so forth, better than the digital logic that we're using today, it may be possible that we could develop basically a way to do policy experiments through simulation in a way that we can't do today. Final thing, and just to kind of finish up, is what would some of the characteristics of these architectures need to have? They would probably need to have runtime specification, so they wouldn't be programmed all the way down into ASIC, but things that could be basically compiled by users at runtime. They would need to be able to accommodate a variety of network types: sparse, dense, random, small world, scale-free networks. Those are the kinds of things that emerge in these applications. The hardware would probably have to be auto-reconfigurable because these networks evolve over time. I'm not trying to get into suggestions for architecture or specific devices or anything like that. I'm just sort of saying, from kind of an application pull point of view, what would need to be done. And design form possibilities, or where would this need to happen? Certainly the supercomputer is interesting, but modelers work they kind of start small. So I would like to see these types of capabilities pushed into kind of coprocessors or processing cards like GPUs, so that individual workers have the opportunity to work with these kinds of things every day. Cluster computing, certainly. Supercomputers, certainly. And then finally, tying back to kind of where we started in the national laboratory, national security, nuclear weapons type of stuff. Many of the applications that I talked about today are kind of getting at what's the central tendency. What is the middle of this population going to experience? Okay, and that might be fine for some of the things I talked about. But when we start talking about national security, we start talking about nuclear weapons, we're certainly interested in the central tendency, but we're also interested in the tails. We're interested in what's happening out there at 4 sigma, 5 sigma. We're interested in, what are the outliers going to be? And to be able to handle that, many of the things I showed today were massively scaled down. You know, we're interested in the national population, but we're simulating 30,000 agents and things like that. When you do that, you lose out the tails. So these simulations are going to need to get, basically to calculate the tails, they're going to need to be massively scalable to very large populations of agents. And particularly if we think about looking at sociocultural effects and partial differential equations and things like that to big international problems like geotechnical engineering to address things like global warming, where we're thinking about modifying the atmosphere, modifying the oceans, we're going to need things that look at social networks and physical issues as well. So anyway, thank you for your attention. I appreciate it.
I can see in many of the examples that you described real possibilities for architectures that are similar to some of those that have been discussed today. But you mentioned Markov chain Monte Carlo, and that one in particular, it seemed to me, we looked at it for a problem ourselves, and it seemed that there was really no effective way to have a parallel implementation other than starting a whole bunch of chains and somehow figuring out how to summarize over the whole population. Is there something that we're missing there? Is there a possibility of a parallel Markov chain algorithm?
I'm not sure. I'm not the hardware guy. You're right that is the memory problem and the forward modeling problem and the Markov chain is all a problem. But again, I'm saying it appears to me that there's a massive application pull for understanding the uncertainties in these calculations, and if these new hardware devices that are being developed enabled new architectures to solve those problems, you may be right that it's not tractable. Thanks.
Let's thank Kurt again.
All right. So,
The last speaker of the day
flip
is
this mic on you,
last speaker of the day is Bruce McCormick
and
from Computational.
you can stick that in your pocket and clip it on your.
And then after that, we'll have a roundtable discussion.
Just give me 1 moment. Get back to that.
So I'm with Cognitive Technologies. I previously was at Intel for 36 years, and I was there during the early days in the microprocessor, and I actually believe that we are re-entering that kind of phase again in the industry for computing in terms of excitement and new things to be doing. And that's why I left to join up with Cognitive. And it's very gratifying to see the interdisciplinary group of people here. It's very exciting, actually. And just so you know that I believe in everything that's being talked about here, some of you are from the universities and with neuroscience background. A couple of you may know my brother, who is a professor of neurosciences. He runs a neurological lab at Yale University. His name's David McCormick, and it's my younger brother. He was attributed for learning how to put brain tissue and keep it alive in vitro so the neuron could be studied while it was still alive. He was also one of the first for tracking out the learning process in a rabbit at Stanford University. And he and his daughter actually entered some contest some years ago where they applied spiking neurons to win a contest at doing speech recognition. So I firmly believe that research is required and all these things are important, and it's in the blood in my family, okay? But when the airplane first got going, it was studying the bird took you down a few wrong paths in the very, very beginning. You needed to focus on thrust and lift. And it wasn't, for example, many decades until really understanding the feathers and how well they modified the characteristics of the flight was applied to fighter jets, for example, for having very unstable surfaces so they can be very nimble. And it's my understanding that a couple of people in the very early days of flight actually died from AFTTE, and I'll just throw that acronym out there, but that's applying feather technology too early. So we'll see if what happens here, right? So just to go a little bit forward, like Lloyd did yesterday, I wanted to share a few of my experiences. In the mid-'80s, early '90s, I was at ground zero with flash memory, getting that off the ground. And that's a whole other story by itself, but there was a sister technology that we had at Intel at the same time, and it was E-squared memory. And there were several different versions of it. But an E-squared cell is a writable non-volatile resistor. That's what it was. You could also think of it as a charge-controlled multiplier, as a memory cell in a linear state. So I got funded at Intel a electrically trainable artificial neural network that we actually put on the market. This was in the late 80s. And it was a 64 neuron device. I think it had 10K synapses, if I remember right. It was fully analog in, it was fully analog processing inside, and it was analog out. Okay? And it was very hard to use, it was very hard to design. It was based on a non-volatile, rewritable resistor memory technology, which don't exist in production anymore. That was a production process at the time. DARPA funded Intel to do an NI-1000. Just to go the gamut here, it was a bunch of processor cores with a topology like a neural network, so it could study and have the flexibility of modifying various things. This is all during that hype cycle that Maikos presented a little bit earlier in around 1990 time frame. And it kind of died off. Okay, so the next thing that everybody at Intel wanted to do is actually what I'm going to show here. And unbeknownst to me at the time, IBM was pursuing a very similar architecture, and this is actually a third generation version of what IBM did. And ironically, the guys at Almaden did not know about this effort that went on about 10 years ago, 15 years ago. And we'll talk about it in a minute. But as a computational person, which my background's been that with hardware and so forth, you don't want machines to exactly do everything that we do. Okay? For example, we tend to forget things, and you don't want a robot to forget the keys like my wife does every morning when it's about to go out into the car. Or we are fairly difficult to repurpose and to transfer our knowledge to other people. And you want a machine that can be very quickly repurposed, as well as the information shared, as well as being able to move blocks of knowledge in and out of an architecture quickly. So I'm going to describe why this architecture actually does that. The other problem, psychiatrists will tell you when we get mentally ill, we are very difficult to debug. And and there's a lot of neural network approaches that are very difficult to debug. You aren't able to go in and figure out exactly what's going on, and that can also be solved. So what I'm going to talk about then is a massively parallel or machine learning implementation into an ASIC for real-world applications that's commercially available now. These products are actually at DigiKey and other distributors around the world. The chips, the boards, software tools, and so forth. And the chip that's shown here on the far left is a 1024 neuron device. It does learning on chip, and I'll go over its architecture in a few minutes. Okay, it implements two nonlinear classifiers, radial basis functions, and k-nearest neighbor, which have been in the software industry and been used for years and years for people for solving pattern recognition kind of applications. We're a direct ASIC implementation of those algorithms. We also have a board that we put 4 of these chips together on each board, and we have a FPGA in between each of the chips. And I'm having trouble with this. Okay, sorry. there's an FPGA also on these boards, and we picked the Lattice one because it's one of the few in the marketplace that's flash-based, so you get dynamic reconfigurability of this architecture at the person who actually uses it. So there's actually a vertical spine through these set of boards to allow connectivity between all these neurons that's also connected through that FPGA, so you can get the flexibility of making recursive architectures or applying little or a lot of resources to the problem in terms of image recognition, video processing, or data processing. So we actually believe the technology has a lot of applications, from sensor type of applications where you do pre-processing. We have a lot of examples on that. And we also are building this system down here of 1 million neurons. We actually would like to put optical connections between the stacks of neurons. This is a 1 million neuron system. This, I believe, is a 20 stack, which is an 80,000 neuron system, to do things like genomics. And we actually we're looking into Graph 500. And I'll explain how you could do something like Graph 500, which is a supercomputing benchmark on this kind of architecture. Okay? And since I came from Intel, I'm going to spend a few minutes on giving you why I believe really now is truly the right time. And this graph up here is well known. You can see that processor versus memory ratio of performance has gone from 1 to 1 in the 70s time frame to now it's over 200 in terms of a ratio. So there is a bottleneck that has been created in the von Neumann architecture between CPU and memory. And also, this has been talked about quite a bit. This is a slide that I grabbed from some people from the high-performance computing world, and they've been graphing things that are reflective of the typical power, the frequency, and the single-thread performance. Those are the three in the middle. And this is the Bernard scaling kind of aspect. So when people talk about Moore's law, this is one piece of it, but it's actually called Bernard scaling. And as everybody knows, in the last 5-6 years, power density stopped, frequency basically stopped, and everybody is basically maxed out on single-thread performance with their architectures. And that's a big change. Okay? So the top curve up there with the red dots is the number of transistors integrated, and that has not stopped. And that's also part of Moore's law. And Intel believes they can see their way clear down to 7 nanometer or so, and they got 14 going into production here. Okay? So the transistors are still doubling, but they can't go any faster. The core voltage is down to a point where you can't go any lower because of noise and so forth. And what are people doing with all those additional transistors? They're going multi-core, and they're putting mini cores together. So you see this with NVIDIA, you see with Intel, you see with DSPs. There's all kinds of startups out there happening where they're putting all kinds of cores together. So this change, though, well, I'll talk about it. Historically, von Neumann architecture has stacks going parallel, though. There's shared and distributed memory issues. I think some of the people talked about cache coherency and synchronization, communication between processes, parallel software programming complexity, coordination of resources. All these things are very, very hard to make happen, whereas the brain solves many of these problems. But one of the key reasons why neural networks never got off the ground and why a lot of parallel architectures didn't make it is Amdahl's law. And Amdahl's law basically favored serial processing. Every time the processor got twice as fast, you were punished if you tried to do parallel hardware when the guy next to you 1.5 years later had the system based on a serial processor going twice as fast from 1.5 years before. And because most of the problem can be done by serial processing. And the only thing that really survived that law was GPUs and graphics, because it was such a naturally parallel type application. It was a big enough market to allow for processors to get optimized in that direction. That left side of that equation stopped. Okay, so now everybody's trying to go get the performance improvements by going parallel, and so that's why it's time. You can get parallel architectures going out here. Okay, so everybody knows in the last century there was 2 paradigms created, and even John von Neumann himself said, ideally one would desire an indefinitely large memory capacity such that any particular word would be immediately available. He's describing associative memory there. Okay, it didn't really exist at the time. So he knew the shortcomings of his architecture, and the natural parallel one with machine learning, particularly embarrassingly parallel type algorithms, eliminates the bottleneck. You can do the search and sort in parallel. I'm going to talk about that in a second. Very low power, parallel programming and communication can happen naturally. All right, and I believe that this path will put us back on the path of exponential trends in computing, actually. And Robert Noyce himself, who co-invented the integrated circuit with Kilby, who was one of the founders of Intel, stated himself personally the von Neumann machine was going to go the way of the dinosaur because random errors will obsolete current logic. And that's because the soft error problem for static logic processes, when you get down to these very fine geometries, are going to run into problems. And they know this is coming, okay? Whereas the inherent redundancy that you have in the brain models actually get around that problem. So this is the architecture that IBM pursued, that Intel was going to pursue after those other two chips I mentioned before. And as I stated, it's a nonlinear classifier of radio basis functions. The learning function is called RCE, or restricted Coulomb energy. It was done by a Nobel laureate, Leon Cooper, who had a company called Nestor. For years and years and years, they sold software renditions of this for solving AI problems in the marketplace, but it was all software-based. This is the hardware implementation of it. But looking at the input could be up to, now this is the way we physically implemented it. There's plenty of variations that can be done, and there's lots of enhancements that can be done. So it's not the end-all for architectures. But on the left, you have a 256 byte, essentially 2 to the 2048 input, and that is simultaneously broadcast to all these memory models or prototypes that you have on the chip. You can call them datas or models or prototypes. and whatever was stored there previously, and I'll get into the learning function here in a minute, performs either the Manhattan distance or the max of the input minus the data model, and then sums it up. So you're getting the L1 or the LSUP is what these are also typically called, but it's a differencing engine here. And I'll skip the min and max here for a moment, but then you go to an output out here where search and sort is done. And in this particular architecture, one of the things that got solved was in a constant 16 clocks, they're able to take n number of comparisons and find out who's the closest one to the input, no matter how many there are, 1,000, 10,000, 100,000, so forth. So there's a hardware trick to do that. Now, one of the things that wasn't put on this chip, which we probably will do on the next generation version, is making a Bayesian statistical classifier out of it. And that's on the output out here. There, you actually get the distance information, you get the category, you get the number of neurons that fired, so you can use that information to do probability analysis, to do Bayesian statistical analysis, essentially. So that could also be done in hardware here, but on that architecture I showed you a little earlier, you could do it in the FPGA. We actually, one version of FPGA, we put in a microcontroller in it, so heterogeneous type of computing can actually be done, as was advocated by Matt at HP yesterday. And we also believe that it's going to be a heterogeneous world for quite some time. The beauty of this kind of architecture is it's very familiar. It's actually in the KNN mode, the data coming into this looks just like any other digital processing system. It's completely deterministic in what's done here, okay? And before you turn on the learning mechanism, and you can actually load in blocks of metadata where you want them to be, and pull them out and swap in and out. And it also doesn't do learning the way neural networks do, where you go with a random weights and then you bring in data and then you start adjusting all these weights, which occasionally won't converge on you. This architecture always converges. And you start out with blank memory and you put in, so let me go through the learning process. And that's where this min-max comes in, which is all hardware embodied in this as well, and it's done automatically. It's done just as fast as the recognition cycle. Okay, so say everything is blanked out. You have a picture of somebody's face. You store it as a 256 byte model. in one location, and you have it set so it's fairly generalized as to how it's going to recognize something coming in. Another model comes in, maybe a profile shot, maybe a little bit different lighting conditions, something like that, or turn face. It compares it against the model that you have. If it's within the region of influence of that particular model, and it says, yes, I recognize it, then that data point is either discarded or held aside. If a data point comes in and says, I don't recognize it, and you say, hey, it's the same category, then you add a second model. And this process continues until you get, okay, I'm going to have a different person I want to recognize. So say a third model comes in, it's a woman now, and they put in the model, or first it's compared to the first two, and you go, is it recognized by the first two? And if it is, then these two are overgeneralized, and it will automatically take this thresholding function here, which is where you get the weight, and adjust it so that these earlier models reduce their influence so it accepts the new model that represents somebody else as a different category. Okay? So that's basically how it does the learning. So the recognition cycle of this is a constant 10 microseconds of flow through. The learning is also a constant 10 microseconds. And so you can learn in situ in the system while you're doing things. And so some of the applications, just taking a look at this, how would you do various applications? Well, for example, fingerprints. Fingerprints, the minutia of a fingerprint, easily fit within 256 bytes. You can store these in these memories here. You can have them up to millions if you want. And then you bring in a fingerprint that you've never seen before on the input. It's broadcast in parallel to every one of them. And 10 microseconds later, you have the match. Okay? No matter how many fingerprints you're comparing against. That's one example. Data deduplication is another example. On large machines, you want to have a hash function stored, and you want to come in with a new file. And you say, is this new file a duplicate of what I've already stored on my drive? And it immediately compares against all of them. For Graph 500, let me go on that example for a second. The way where you have edges, and you look at how many gigateps or the edges that you can transverse per second. You have vertices and the edges, and you have parents and child relationships in graph theory. So you can take an edge, bring an edge in, the vertex, put it in here, the next vertex comes in, and you see if you recognize it. And if you don't recognize it, it'll learn it as a unique vertex. So you can store in here, again, unordered, non-tagged, non-indexed, all the vertices that are unique, and then come in with a root vertice, and then it'll immediately give the match, and the category can point to all its children. And that could be done in nanoseconds, actually, with improved speed on the architecture. And you can, with advanced lithography, we can easily see our way clear to getting 1 billion of these neurons or more into a fairly small system. Okay? So this is the basic architecture of the machine. And I talked about some of the applications here, but data clustering, for example, you can learn information, see whether it's in the same category as something you learned before. If it doesn't match that category close enough, it gets its own category, and now you have an anomaly or a new cluster that forms. So you can actually go through data that has not been organized and cluster it, for example. We talked about biometrics, face recognition, things like that. Pipeline data flow processing. So we looked at this in quite detail at Intel, actually, for packet processing. And there's a variant of this kind of architecture where you can actually, in one clock cycle, be able to look at a string of values with wildcard capability, which you typically have in packet processing, and find out if there's a match or not. So you could be looking for specific content information or signatures in the headers, or you can also, in a fuzzy way, be looking for behavioral changes and try to catch something as it's morphing. You know, for example, people morph code, and they reorganize the code, or they put in dummy code, for example, to get around cybersecurity kind of screens. You can catch that kind of activity with this kind of thing. MPEG-7 is something that was actually defined to be implemented by neural networks. and it's never really been implemented. But it's a set of specifications for audio and video files where you really do need to have neural network kind of processing to effectively do it. So this is a future application I believe is going to be used with the technology. So I want to step through just a few demos here. This is a screenshot of the fingerprint. You can see this in the back of the room that we have. And on the left, we have a simulation run on a computer of 320 neurons, 3,200, and 32,000 neurons. And you can see essentially the von Neumann architecture. It scales, in fact, exponentially gets slower for handling the number of neurons that you're, pardon me, what it is a fingerprint recognizer. You give it a fingerprint and it's comparing it against 320 examples or 3,200 examples or 32,000 examples. And you can see the effect of it there. On the right-hand side is a hardware-based system. It's actually the hardware sitting in the back of the room with 32,000 neurons or 3,200 or 320. And you can see the results are constant. It's the same amount of time. In fact, the time here is actually getting the information displayed, not the computing time itself. And you've got roughly 3 orders of magnitude here. With this is a 130 nanometer lithography chip running at 27 megahertz, by the way, compared to a multi-gigahertz notebook. So even with that, you got 3 orders of magnitude performance advantage here. And this was done in about 6 watts on the right, and this is like 60 or 70 watts. So you got 4 orders of magnitude of performance per watt improvement here, okay, on doing this kind of thing. And that's, which gets even higher when you get to much higher numbers. Here's another example for signal processing. This one to me is a fascinating one, but this is an EEG waveform here. And a doctor, people talked about, hey, people, when they show you something, you immediately recognize it. We had an example of 20 pictures being flashed at us. We immediately knew what they were. Well, a doctor can take a look at this waveform, and he knows, just looking at this, this hitch right in the front of the waveform here, it's an EEG waveform, that this is an epileptic signature, okay? And it's very quickly recognized to him. And if you give this problem to a DSP guy, he'll take man-years of effort of doing signal analysis to try to get the right frequencies and so forth to be searching through to find out exactly whether or not that waveform is there. This system used only 2 neurons. To go in actual production, it takes more like 10. Okay? And it only took seconds to actually train the system to do this, to recognize where the epileptic signature was in the waveform and mark it throughout the entire waveform all the way to the clip being removed from the person and the signal dribbling out. Okay, it was still correctly identifying it. So it's just another example. We have on our website a paraplegic that is using the technology for learning how to move his legs. We have an example of adaptive optics where a military installation over in Europe removed a supercomputer and used one of these chips to do adaptive optics for beamforming. So it's another example. This particular one, all this shows is just, okay, you're training it on this person's nose, you hit learn, and then it's track. And what is happening here is this person's moving. You can see that the neuron count here is slowly growing. And that's because what it's doing is learning as the person's moving around. So we have application examples of tracking cars going underneath a bridge, and they become obscured for a period of time. They come out on the other side of an overpass, and then it picks it up again. Same kind of thing, where you learn the object as it's moving. And so if you go back to the architecture, the way that's done is by looking at the distances and seeing if they're starting to get too far away or the number of neurons that are firing. If too many of them are not firing anymore, you say, hey, I've morphed too much. I want to go to the next, I need to learn a new example. Okay? So that's a couple examples. This is another quick and dirty one we did with a Microsoft Kinect. And hopefully that doesn't. Sorry. Yay, Microsoft, right? We have these videos out on Cognitive YouTube, by the way, so you can go and look at a bunch of these. But we're using a Microsoft Kinect as the 3D sensor, and we're trying to do some real-time action recognition. So grabbing the dice, shaking the dice, then passing the dice. This was actually done to impress some people in Las Vegas that they were looking for gambling tables to have a hands-off kind of functionality. Okay, so I'll go to another example here. Just for doing video surveillance, it is very difficult for low-end cameras to be able to detect whether it's a person that came into the room versus a large pet. So here we're just doing simple frame subtraction, and we have a set of models that recognize the person, and so far we haven't found a false positive yet on recognizing dogs from many different videos. We actually have some burglary type videos taken off the internet, and it works pretty well. And this could be done for the number of neurons we're talking about here is about 90 neurons. So you could do this actually for about $1 and put it into a surveillance camera. Okay, just one more on the Kinect, just doing hand signal gesture recognition, where you can train it to do. This works with anybody walking up to it, and we actually have the hand being used as a mouse, and you can see how noisy the input is. That image that's being shown down here is very noisy, and that's the input that this system is using to recognize what's going on. So just another example. This example is a bunch of kanji characters, and hopefully it runs. We'll see here in a minute. But there's like 120 kanji characters. Kanji is a pictorial language. It's relatively difficult to recognize, and I think we may be not running. But we do an exhaustive search through this on simulation mode. The stopwatch times it out. It also shows the sequentialization, and it goes. It takes about 3 minutes to go through this on a simulation on a computer to scan this entire thing and identify all kanji characters. It's using like 360 neurons to do this, 3 neurons per character, and when you apply it to the hardware, it does it in 3 seconds. So it's 60 times faster, and it's about half a watt versus 10 watts. So you've got 20 times lower power. So you're around 3 orders of more magnitude at 360 neurons faster than a CPU. So, so we have plenty of other little examples that we have in the back of the room. So this shows plotting a chip like this on those curves we showed a little bit earlier. It's 1,024 cores effectively. So you jump up the parallel curve. It's really memory. The memory is doing the processing. You're getting rid of all that moving information in and out of memory and not fetching instructions. Okay, so anything that's embarrassingly parallel, by the way, that you're doing over and over again, you can implement in the memory without too much overhead. In fact, in this particular chip, it's a 30% overhead over the memory for doing all this calculations and learning functions. So it's not that much of an overhead, but it's done massively in parallel, and it's low power as a result. And the X up there is the, excuse me, it's a 27 megahertz, so that's what the X is, and then the triangle at the bottom is its max a half a watt. This Beyond system that we were building, 1 million neurons in parallel. This is less than a cubic foot here, and again, it's on an old lithography. We can make that one chip. If somebody had the wherewithal with the money to go to around 20 nanometer kind of process technology, and it performs 0.13 petaops in about 200 watts. Okay, and the way that's measured, by the way, it's not flops, and these are byte integer operations. So I want to be clear about what we're doing here. It is 1,000 chips times 1,000 neurons on each chip times 5 operations that are done in parallel. It's a compare, a multiplex, subtract, an accumulate, and a search and sort, which actually takes more operations on a normal computer than just one. And it doesn't have a load and store, so it's at least 5 operations times 256 times 100,000 of these per second. So earlier, Tarak was talking about some of the calculations and performances he showed with different CMOS implementations of digital versus analog. This lines up exactly right on his table, comparing GPUs and CPUs versus what could be done in this kind of architecture. Okay, so who cares about 1 million neurons, right? So people like going after studying the brain so much. The bee has about 1 million neurons and about 10 to the 9 synapses. And it's known that a bee's nose is so precise it can distinguish between hundreds of different aromas and tell whether a flower carried pollen or nectar, sifting it from quite a ways away. It can fly. It's got the ability to see through 2 eyes and do 3D rendering real time and operate in a group, as well as it can solve the traveling salesperson problem. And that's also been proven. So they can randomly figure out how to fly in the most optimum way from one flower to another. And this is with 1 million neurons. Okay? So just studying that and modeling that could give a lot of capability to a lot of applications that small autonomous flying machines, for example. So future possibilities, as I mentioned, it's on a 130 nanometer process versus, so it's 5 generations back. You can get several orders of magnitude of performance per watt improvement by going forward. Just staying on a static logic process can get you to 100,000 to 1 million neurons per chip. You can easily get up to the 500 megahertz to gigahertz range, somewhere in the 600 to 800 megahertz. And 1,000x can give you 1 billion processors in a very small footprint. Okay? And another thing that can be done, I'm absolutely a believer in non-volatile technologies. Like I said, I was at ground zero in Flash. And I believe in E-squared memory being the right thing for neural networks. And so these newer technologies like memristor and phase change memory, I agree with and believe in. MRAM is a possibility as well. So, and people know the statements that HP and IBM have made in the press. So that's not news to anybody here. And I already talked about parallel processing and serial stream architecture. We're actually working with University of Hawaii on genomics as well. Summary is the size of digital information is growing and access is increasing. We need more intelligent solutions for managing and protecting this data. Adaptive parallel pattern recognition is the way to get there. The physics ran out of gas on some of the scaling aspects, and it's time for technology like this to get going. So there's lots of things to be done, and I actually believe the industry is going to get restarted. So that's why I'm still at it. Okay, thank you.
Good question was your introduction. So you have a single layer network.
What's it? Well, it's a 3-layer network. That
Inputs, outputs, I guess.
it's the equivalent of a 3-layer network. So the question was, it's a single layer network. No, it's a 3-layer network. It's been shown to solve exclusive OR. And you got an input layer, you have the weight function, and then you have the search and sort as the output layer, basically. So it's mathematically equivalent to a 3-layer network. You can stack it, make it 6-layer, 9-layer, whatever you want to do, just by going from the outputs of one to the inputs of another. You can go into recursive if you've got the guts to do so, but it's mostly set up for feed forward. Okay, and my understanding of radio basis functions is that you can implement any nonlinear equation in a series of radio basis functions. So I've seen plenty of papers where people do tsunami modeling, weather forecasting, using radio basis functions. And so you can learn an equation with this architecture as well. So in fact, that's what the guys with the adaptive optics did. They trained it on an equation. Doing things in a temporal way, you need to feed the outputs back to the inputs, but there's things that you can do to enhance that. So, sorry, I need to make that clear. So, it is a 3-layer network, yes. Actually, there are chips out there right now sorting fish on Norwegian fishing vessels that were trained by the fishermen to sort between mackerel and herring and determine the quality of the fish, whether or not they can go into a filleting machine. And the thing is saving them about $1 million per boat per season. and because they can reduce their staff and they can do faster and more accurate than a human can do it. And we have a video of that on our website as well. These guys would kill you if you tried to take away that system off their boat. So, but there are a lot of practical applications in the near term are machine vision oriented, machine inspection, anomaly detection, like you're looking for imperfections in a glass, or looking at a piece of wood and the texture of it, has it got too many knots in it? Those are things that we know we can solve. So anyways, okay. Any other questions before we?
Session going.
All right, thank you.
Thank you.